So let's have a look at some induction questions where it starts to involve some fractions and proving that a series with involving fractions is equal to some sort of sum. So we want to prove that this time 1 times 1 plus 1 times 1 over 1 times 4 plus 1 over 4 times 7 and all the way through to our general term of 1 over 3n minus 2 3n plus 1 gives us a sum that is n over 3n plus 1. So all those would sum to give us that sum. So the first step we'll go is like, okay, let's prove it's true for n is equal to 1 again. So we sub in 1 and there in those two for those two terms. We get the 1 over 1 times 4, which gives us a quarter. Sub in 1 there, 1 here, so we get 1 over 3 times 1 plus 1 gives us a quarter there. So it's true for n is equal to 1. So this time we want to again assume n is equal to k. So we put in our sum to the first k terms our sum of the first k terms is equal to that statement. Again, that's what we're going to use. So we have a look at step 3. What are we requiring to prove? Okay, we're going to put up to k plus 1 terms there, and we're going to have k plus 1 in there and k plus 1 there. So we get a statement that looks like that. So that's what we want to prove. Again, we're going to start with our left-hand side. So that's what our sum looks like when we go up to k plus 1 terms. So up to the k terms, we know that amount would be equal to that sum. So that's where we're able to make that substitution. And all that is equal to k over 3k plus 1 from step 2. Now we want to add the term here, and it's been cleaned up a bit. So 3k, 3 minus 2 gives us the 1, 3k, 3 plus 1 gives you 4. So to do that, we've got to get a common denominator because we've got two fractions and we need to get a common denominator. So our lowest common denominator would be 3k plus 1, 3k plus 4. So multiply this fraction here by 3k plus 4 on the top and bottom, get our like term and get our common denominator, and we can add the tops together. So k outside of 3k plus 4 plus 1. Can't factorize, so let's expand it out, and we're going to, again, we've got a quadratic, so it's not too bad. Keeping in mind what we need to do, we want to get a k plus 1 on top. So if we see what we've got with our factorization here, we get a 3k plus 1, 3 and k plus 1 there, which means we can do some cancelling. That will cancel out. Gives us k plus 1 on 3k plus 4. Now, if we look at our decomposition, we can see that 3k plus 4 would be the same as 3k plus 3 plus 1, which means I can factorize 3 outside of k plus 1 plus 1. And we've got what we wanted to prove. So it's true. And so by step 4, we've proved it by induction. Let's have a look at another example. 2 over the 1 times 3, 2 over 3 times 5, 2 over n, 2m minus 1, 2m plus 1. So we've got that statement, and that will equal to that sum there. A little bit different, 1 minus 1 over 2m plus 1. So again, let's sub in 1 into the nth term there, and we get 2/3. We sub into 1 into our sum, we get 2/3. So it's true for n is equal to 1. Sum of the first term is equal to that statement with 1 in there. So it's true there. Again, assuming that n is equal to k, this whole statement here is equal to 1 minus 1 on 2k plus 1. So step 3, we want to prove that it's true for n is equal to k plus 1. So we need to get a k plus 1 in there for n. So what are we requiring to prove? We want to prove that we get this statement. So the 2k plus 1, or that can be simplified down to 1 minus 1 over 2k plus 3. So we that's what we're looking to prove. Can we do it? So we get out some of the first k terms plus the k plus 1 term. That statement there we want to get rid of because of those, we don't know how many terms we got, but we know that it's equal to 1 minus 1 over 2k plus 1 from step 2. That's our sum of the first k terms. We've cleaned up the k plus 1 term, so 2 lots of k plus 1, 2k plus 3. So that's cleaned up a little bit there. Now what we want to do is start to add some add the common denominator, get a common denominator and add there, because we want to come down to a statement like that. Now notice we want a 1 minus, so what we're going to do is leave the 1 minus by itself. It's already there, so why play around? Why do we don't need to get a common denominator here, because we want 1 minus something. So notice the 1 minus stays all the way through. It's not going to matter to us there. What the trick we've got to look at here is we've got to get the 1 over 2k plus 1. So when we put it in the brackets, we're factorising the negative out. So notice it's plus here, but the term starts to be negative here because we factorise the negative because we've taken the 1 minus and then we've got everything else in a bracket there. Because again, we want to work at something like that because we want 1 minus some whole statement. So we want to start playing around with that to see if we can get down to what we're requiring to prove. So factorise out, factorise the negative out so that becomes positive, factor out a negative there so it becomes negative here. Now get our common denominator. We've got the 2k plus 1, multiply top and bottom of this fraction by 2k plus 3, which is what we've done there to get our common denominator. Again, expand it out, clean up our terms. 2k plus 3 plus minus 2 means we get 2k plus 1. We've got 2k plus 1 on top. They cancel. Gives us 1 over the 2k plus 3, which we saw that would be nice enough to prove because we know that's equal to 1 minus 1 over 2k plus 3. So there we go. It's true. We've proved that it's true for n is equal to k plus 1. So by step 4 again, we were able to say, yep, it's all true for all those different all the positive integral values.